Hello everyone, welcome once again to Supervised Machine Learning Zero to Production with Pierre with Mike. In this video, we are going to be discussing about loss functions and why models learn. When you call model.fit in Scikit-Learn, which we are going to eventually see, right, something happens. The model gets better at predicting, but what does better mean? And how does the model know which direction to improve? The answer is in the loss function. This is the thing that defines what wrong means for your model. And it is the engine behind all of machine learning. So let's go to our whiteboard. Let's say we have a data point. Let's get a data point here. A data point here. Let's say we have this here. And let's say we have this here. Let's say this is our true prediction, our true value rather, which is our y. Let's increase this, which is our true value. And what does this mean? Let's say we have a set of data. I think we have a set of data here, right? And let's say we are trying to predict if it's a car or an airplane. Or let's just get let's get this. Let's create let's proceed with this, right? So let's say we are trying to predict the weight. Let's say this is not our label for now. Let's say this is our label. We're trying to predict the weight: 20,000, 7,910, 4,000, 40,000, and the likes. So let's say 20,000 in this instance for a single record or a single row in our data is our true value. We then have another one here, which is our predicted value. Like let's say when we are training our model or when we've trained our model, predicted. But the difference here now is that we have like something on this place, which we call y at. So y at is our predicted value. So let's get this. Let's get an arrow. Start from here and stop here. Okay. So and let's say we have this. Let's say we have this. So this is our error right here. And we then have our loss as loss is equal to the rate of change, between y and y hat. Let me put the hat on top of it so we don't mix those up. Okay. So let's expand this. So that is our loss. So the loss function in this instance converts that error into a single number, the error between this y true and the y predicted. Convert it into a single number. The model's job is to make that number as small as possible. The loss function is how we score the model's wrongness. Give me a prediction, give me the truth. And the loss function returns a number, small number. When the number is small, the model is close. When the number is large, the model is far off. And in that instance, let's say when we have our true value as 20,000, let's say we have about 19,000 predicted, right? The model is close, but let's say we have about 40,000 predicted for this 20,000. Then the how would I call it? The number is large, which means the model is far off. So let's say let's bring this here. Let's say our true value is 20,000. And let's say this predicted, how would I call it? Predicted, that is 19,000. So what does this mean? This means that the model is close. Why? When we compare the error between 20,000 and 19,000, right? In this instance, it is not that much, but that is not the actual calculation, but it's just to give us an intuition behind it. But if we get a predicted of like, let's say 40,000, right, that means the model is far off. It's far off, which means our error is high. Which means our loss is high. Okay, so large number during training, the model adjusts its internal parameters to take this number to, or actually to make the number, the loss smaller. Which, so now let's also take a different plot here, so we can just get the intuition behind this. So let's have an arrow. Yes, let's have an arrow. This comes here. No, this comes here. Oh, I didn't pick an arrow. So let's have this. Let's pick another one, and let's have this come like this. Okay. Yeah. So now let's now assume that we have this. The bell shape is one of the best intuitions so far of our loss. So let's say we have this. No, that is wrong. That is not really bell shaped. Oh, I think we are close now. Okay. So for this now, let's say this is our model parameter. And this is what? This is our loss. So what does that mean? Somewhere around here, okay, let's pick this. Somewhere around here should be where our model should be an optimal loss point for our model, right? And why do I say that? Because now, as this go higher, that means the loss is higher, either on this point or this point. And this, like, kind of, this is like one of the areas where we have the lowest loss value, right? So now, let's assume that as our model is learning, if it starts here and it takes a very, very large step to move from here to here. So let's take this once again. So what does this mean? This means that the model took too large a step, which means it will take more iterations to actually, or it might even overfit or not even generalize well, because it's supposed to take small steps optimally. Like, instead of starting like that, let's say it started like this, stop there, let's get this, and it continues again to come from here and stop here. So the intuition is that you want to start with, and now there's something that we need to make clear here. You see, these steps, either big or small, that is happening is what we call the learning rate that affects our loss value. So what does that mean? A learning rate too high, which means your model will take it might not generalize faster, it might not learn from the data faster. But, and even when it's too small, like let's say it's starting from here, it stopped here, it stopped here, it stopped here, too small also means the model will take too long to actually get to an optimal point in this slope, right? But finding a middle spot for it is one of the most important ways to get this to work. So, which is what the loss function helps with during training. So the model adjusts the model adjusts its internal parameters to make the loss number smaller according to the learning rate. So it updates the learning rates as it proceeds. So this bowl is everything. Training a model means finding the bottom of this bowl, which is what we have here, for example. The loss function defines the shape of the bowl. Different loss functions give different bowl shapes, and that changes which solution the model finds. So let's proceed to discuss about regression loss. So mean squared error, as you can see here, means we are taking like a squared error, a mean of the squared error of our actual values and the predicted values. For example, let's go back to our whiteboard. Let's tag this regression losses. Okay, so let's say I want to predict on 3 values. Okay, let's pick it here to make it make sense. Let's say we are trying to predict weight. We have 20,000, we have 79,000, we have 10,000, we have 40,000. So 20,000, 40,000. Let's take this. 20,000, 40,000. Okay, let me know this command. 20,000. What else is there? 79,000, 10,000, 79,000, 10,000, or let's say 10 before 40,000. So let's say these are the values that we are trying to predict, right? And let's assume that we have the first the model predicted 25,000 for this, predicted 76,000 for this, predicted, let's move this so that we can all no. So let's say it predicted 12 for this, and it predicted 49,500 of 39,500 for this. So this is how the mean squared error works. We take the difference, or the difference of the squared error. Like let's say we take 20,000 minus 25,000 all squared, yes, or let's just use this to represent all squared. Then let's confirm. Then what this means is we have to sum these square differences. So plus, what's our next one? Let's move this so it does not cover it. Okay, plus, it's still covering it. Okay, plus 79,000 minus 76,000 all squared plus 10 minus 12 all squared plus 40,000 minus 39,500 all squared. So we then take it divided by, how many do we have? Divided by 4. right? So this is how the mean squared error works. We take a square of the difference of each predicted and actual values for us to get the mean squared error. Now this is smooth, differentiable everywhere, easy gradient descent. You use this when you have clean data with few outliers. So you won't the Scikit-Learn package already makes this easier for us, so you don't have to compute this by hand. It's just for us to get the intuition behind all these metrics. We also have the mean absolute error. The difference between the mean absolute error and the mean squared error is that you don't square this. You don't square this. You just compute the difference, the absolute difference. So what does that mean? This does not become minus 5,000. It is actually 5,000. This, so that is the absolute, the mean absolute error. So this is robust to outliers, linear penalty. It is not differentiable at 0 and harder to optimize. You use this when you have data with outliers that you cannot remove. We also have something called the Uber loss, which is like the best of both, smooth for small errors and robust for large. What it just means is you have one extra hyperparameter to tune, and you use this when you have real-world messy data, which is often the best default. So we'll be going now into classification loss. So in classification loss, you cannot use MSE because you are not trying to predict continuous values. You cannot use MAE and the likes. So we have log loss. The reason for not using those is subtle but important. In classification, the model outputs a probability, a number between 0 and 1. You want to penalize confident wrong answers much harder than certain wrong numbers. MSE does not do this, or MAE does not do this. Log loss does. So what is log loss? Log loss is when you take minus 1 over n, again still boils down to averaging, times the sum of, so which means you are taking the sum of y log predicted, okay, let's say y, which is our actual value, multiplied by the log of our predicted value plus 1 minus y times log of 1 minus our predicted value. So you take the sum for every actual and predicted value. You do this, you then take the sum and you divide it by the number of your representation. So for when you have a correct and confidence prediction, that means you have a probability of, like, let's say 0.99, and with a true label of 1, the loss is very small. But when you have a predicted probability of like 0.60, which we would all see, it's still okay, right? But the loss is medium. But when you have a predicted probability of like 0.01, that is catastrophic. So this behavior is exactly what you want. If a model says it is 99% sure that the patient does not have cancer, and they do, the model should be a very large error. Log loss captures that. So we'll be going into gradient descent. So how does gradient descent work? You start somewhere, which means the model initializes with random parameters, like let's say a learning rate of like 0.01. You compute the log loss. How long is the model right now? You compute the gradient, which direction increases the losses. Then you step opposite if needed. If that direction decreases loss, you repeat until loss keeps decreasing, which means your model does what? Your model converges. You don't have to worry about this. Again, we are just trying to get the intuition behind all these things. Scikit-Learn handles this internally. You set the learning rate hyperparameter, which we are going to tune in our subsequent videos. So let's go back to our bowl to actually better understand this. So the learning rate controls how big each step is, like I explained. Too large, you overshoot the bottom and bounce around. Like let's say it comes here, it tries to go back again, it comes back here, it tries to go back again, it comes back here, and the likes. And that affects your model from learning. And when it is too small, like I said, like let's say instead of moving from year to year to year to year, right? It moves from this place to this place to this place to this place and the likes. It means your training takes forever. This is one of the hyperparameters, again, the learning rate, the hyperparameters that we are going to tune in our subsequent videos. For now, know that Scikit-Learn handles gradient descent for you internally. You set the learning rate and it does the rest. The entire step of starting from somewhere, which you set, it then proceeds to compute loss, compute the gradient, step opposite if needed, if that's the direction that decreases loss, and repeat until, so that repeat is like, let's say, in the term of when the learning rate overshoots, it comes from here, comes to this place, it sees that, oh, the error is still high, it tries to go back, but the learning rate is still high, so it comes back again, it comes back to this kind of place. But when you start from here, and even if you come here, even if it is not this small, even if you come here, right, it can see that, oh, I need to go back a bit and things like that. So the Scikit-Learn will proceed from there to adjust your learning rates for you to get the minimum loss that will make your model learn from the data. So let's show how loss appears in Scikit-Learn code. So let's go into our code. Let's just have a sample file here, which we are going to update. Scikit-Learn use .py. We then do something like from Scikit-Learn. Since we already installed Scikit-Learn in our previous video, from Scikit-Learn .linear model import SGDRegressor. Again, you can only know this if you have used the libraries. So we then just a sample, right? Model is equal to SGDRegressor. Then we say we want our loss to be what? Squared error. Then we then say our model, you can, for that is for our mean squared error. You could also say SGD loss is equal to what? U bar. But we'll be leaving this for now so that we can test with squared error for now. So you can then say Scikit-Learn the linear model. You can import logistic regression too. Scikit-Learn the linear model, import logistic regression. This is for classification. Logistic regression. Then you can then say CLF is equal to our logistic regression, which is for classification. So let's tag this classification, and for this is regression. There is also linear regression for regression, but this is for logistic, is for our classification problem. So we can then say from Scikit-Learn the metrics import log loss. So we can then say x true, which is our true values, just for us to test this, is equal to, let's just use small values for now so we don't have to pick those from our 1011. We then have our y. Let's assume that these are predicted values is what? 0.9, 0.1, 0.8. This is actually y true, our true values. 0.8 and 0.3. So what does this mean? These are my true values in this case, and these are my predicted values. So let's compute. So print log loss of what? Our y true and y pred. Okay, so let's run this. Let's hope we don't have bugs. Python sklearn use.py. So the key takeaways, right, in this is that log loss functions define what your model is optimizing. Gradient descent is how it gets there. Together, they explain why model.fit works. In the next video, we are going to start getting our hands dirty, collecting all data from cargo and loading it with pandas. So let's go back to our code. This should not take this long. Okay. Let's clear this. Okay, so this should show us our log loss prediction, which we are going to see in our next video.